This topics has its own particular issues. The supernova neutrino detections, when it happens, we will have a lot of events. But we don't know when will be the next supernova, the galactic supernova. The second topic, diffuse supernova neutrinos. The neutrinos are already around us, but it's very hard to detect because they are not very energetic. And finally, high energy neutrinos. They have been detected in the last years, and it's a very interesting topic that we will hear about in the following years. Okay, so starting with supernova neutrinos, we know that theoretically and experimentally that supernova produce high luminosity neutrino flux. And 99%, probably you heard these numbers, 99% of the energy of the supernova when it explodes, go into a neutrino flux. A lot of electron neutrino flux, but also because of the admixture of neutrinos, a lot of muon, tau neutrinos and antineutrinos. The neutrino productions comes in different processes. I will not go into the details of the process, but the time scale is milliseconds to seconds. The production of mainly electron neutrino on the early phases, and then all the flavors in the last phases. And this is the production that we expect from the supernova, from the collapsing star. So since, as I said, 99% of all the energy of the supernova goes into neutrinos, so the flux of all these neutrinos are very intense. They have different characteristics, the electron neutrino, anti-electron neutrino, and other flavor neutrinos, because these neutrinos, during some part of this process, are trapped inside the supernova. We always, when we introduce neutrinos in these seminars, we always say that they are very hard to interact. We should have, I don't know how many millions light years of lead to detect one neutrino. But inside the environments such as supernova or the early universe, the densities are so high that the neutrino interaction is very common, and actually they are trapped inside the supernova. So they thermalize with the supernova environment, and so the spectrum of these neutrinos, of this neutrino flux, is a thermal spectrum. And as the supernova cools, these neutrinos, what we call neutrinosphere, which is the region where these neutrinos are trapped, it shrinks, and the first ones to escape this neutrinosphere are those neutrinos which does not interact with electrons, for instance. So the non-electronic part of the neutrino flux decouples when the supernova is still hotter. As it goes, as the supernova slows down, the electron antineutrinos and the electron neutrinos also escape, and so the one of the ingredients that we can determine about this neutrino flux is that the typical energy of non-electronic neutrinos are higher than those of electronic neutrinos, just because of the time of which they escape of the supernova. Right. So this is one of the ingredients when we think about detecting these neutrinos. We should take this information into account. And the typical spectrum of the neutrinos, it's here. One is a three-dimensional plot. We have the time of the neutrino emission, 1 second. We have the flux and the energy. The energy of the neutrinos are typically around 10, 20, 30 mega-electron volts. It's a low energy neutrino in comparison with accelerator neutrinos. It's slightly higher than solar neutrinos and reactor neutrinos. The luminosity, as I said, is very high, but anyway, this doesn't mean much we have to translate this number into the detection rate we can obtain in terrestrial experiments. And the time scale, this spectrum is not uniform during the emission. We start by, the supernova start by emitting the high energy part of the spectrum, then goes to the low energy as the supernova cools down. And this would be, we can make these calculations to have some idea of the production of the neutrinos, the flavor structure of the neutrino flux from the supernova. But of course, this is not the whole picture, because we know neutrinos oscillate. So even if we produce that very clear electron neutrino, anti-electron neutrino, and muon and tau neutrino flux, we know that during the evolution of the neutrino, something happens very similar to what happens, for instance, in the solar environment. The solar environment happens on this region here. I will not go into these details, but this is the usual oscillation paradigm, where for instance, the electron neutrino, if we are talking about solar neutrinos, they are produced here in some electron density. Mainly, the admixture is such that all the electron neutrinos are produced as an E2, one of the mass eigenstates, and as it evolves to lower densities, then you can have some production of electron and muon neutrinos. This is a very graphic way to understand neutrino oscillations. This happens inside the sun, but then the supernova, of course, we have to go to much higher densities. So we have this whole picture here for normal uninverted hierarchy, where you have two resonances on the neutrino conversion, and we can go to negative values of the density, non-physical, but then we remember that we are talking, if we are talking about antineutrinos, the potential flip sign. So we can, in one plot, see what happens with antineutrinos and neutrinos, or in inverted hierarchy here, antineutrinos and neutrinos. Depending on each of these situations, you have 1 or 2 or 0 resonance on the neutrino conversion. But anyway, this is quite forward to calculate. From those initial flux, what would be the probabilities of conversion, of flavor conversion of the neutrinos, to get the final flux of neutrinos divided into the different flavors. However, we are talking about supernova, and we already saw yesterday on my last seminar, that when we go to very high densities, things are much more complicated than the usual conversion mechanism that we talk about when we talk about the neutrino oscillation on sun or atmospheric neutrinos or long-baseline neutrinos. Because we have this new ingredient that connects neutrino, the neutrino conversion to the neutrino densities. This is where things get nonlinear, and I already talked a little bit about this when we were talking about oscillation, neutrino oscillation in early universe. Here we have extra complications because this interaction, neutrino-neutrino interactions, depends on the direction of the neutrinos. And the environment, the supernova environment, is a very non-trivial environment because you have neutrinos coming from all directions and interacting, and you have to solve an equation which is non-linear and intrinsically three-dimensional. So it's very hard to do it. It's impossible to do it analytically, and it's very hard to do it numerically. And as far as I know, nobody has a complete understanding of how this conversion mechanisms is happening inside the sun, inside the supernova. Sorry. Because usually you make some approximations to, for instance, we can think about all neutrinos coming on the same direction, then you reduce the dimension of the problem from 3 to 1. But we know we are we are taking some shortcuts that maybe invalidates our results. But anyway, since we don't have yet the recipe to make the full calculations, we do what we can. And we know anyway that the conversion mechanism of neutrino flavors inside the supernova is very complicated, very time consuming to do it numerically, very hard to find any analytical light to guide the calculations. And when some results that the people are getting from this evolution is that initial flavor of electron neutrinos and non-electronic neutrinos gets converted in a very non-trivial way. For instance, we can have things like partial flavor swap. An electron neutrino flux can, starting from certain energy, swap to non-electronic neutrinos. Or if we are talking about antineutrinos, a full flavor swap of electron and non-electronic neutrinos. We can have collective oscillations because all of the neutrinos, since the densities are very high, the neutrino-neutrino interactions lead the conversion mechanism and they go together, all the flavors. So it's very hard to make a clear prediction of what would be the neutrino flavor of supernova neutrinos here on Earth. And then to be completely honest, I think it's safe to say that we don't know the flavor distribution of supernova neutrinos. And when we don't know what the flavor is, when the theoretical physicist doesn't know something, then we have to wait for some experimental signal to help us to do the next step, right? But anyway, we have what can make us a little more confident that we can make some progress is that we have already a supernova event, a detection of supernova neutrinos, which is the famous SN1987 supernova burst. And we have this few events, not many events, but we have some time scale of those 10 to 15 seconds and some energy around 5 to 50 megaelectron volts, which is what we expect from the theoretical calculations. One interesting thing that we can look here, and I think it was in one of those exercises that André, I think, proposed, is to look for the dispersion in time, or compare the time of arrival and the energy of the neutrinos. Correct me if I'm wrong, but I think one of the exercises asked to put some limits on the neutrino mass based on that information. Because if you have to be generous about this interpretation, but the high energy neutrinos arrive at the detector first, and the low energy neutrinos arrive at the detector later. We have to be generous because we are mixing two detectors here, IMB and Kamiokande, but anyway, this structure is present there. So in principle, we can do, and people have done that, to get limits on the neutrino mass from this data. Of course, again, not a lot of data, so a lot of uncertainties, but it's not just an exercise to present at workshops, but it's a research that has been done, and you have a limit on neutrino mass coming from this data based on that idea. And you have the distribution here of the energy of the neutrinos on both detectors. The Kamiokande saw more low energy events, and the IMB saw more energetic events. And anyway, this is what we have so far, but now we have to make the next step. So now it's time to wait. Again, I'm being very brief about the the mechanisms inside the supernova, but there is a lot of discussion now to improve the theoretical predictions about the supernova neutrinos before, so we can be completely ready to the next supernova, galactic supernova. Because the next galactic supernova will provide much more events. Remember that the supernova 1987 happened before the large neutrino experiment. It happened before Super Kamiokande, SNO, before Dune, of course, and anyway, before all these high statistics neutrino experiments. So if the supernova, the same supernova that exploded, that arrived here in 1987, arrived now, we would have thousands of events instead of those tens of events that we got in 1987. So a lot of things will happen, and this has to happen in some time in the future, because we know supernovas are exploding everywhere, every time. The problem is that we have to detect these neutrinos from supernova, they have to be close. They have to be on our galaxy, or the case of supernova 1987 in the neighborhood of our galaxy. So we have to wait, and the prediction is that one supernova on our galaxy will explode every 50 to 150 years. So, okay, now it's time to be optimistic or pessimistic. The last one was 1987, so 1987, 30 years has gone. So, okay, we can now start to wait for the next one, right? And when this happens, some things will happen. I think the first thing will be a strong conversion of physicists into supernova neutrino specialists, because we will have a lot of data to understand and an open question to answer about the mechanisms behind the neutrino flavor conversion. Probably, I'm being quite conservative, I believe. More than 200 articles in the first month after the supernova. We will have dedicated conferences in very nice places. So it's something to be aware of on our field. And to be less cynical, we have a lot of learning opportunities from supernova. Okay. This is what I had to talk about supernova neutrinos, and fortunately, now it's time to cross the fingers and wait so it happens during our lifetime. Okay. So the other idea also about supernova neutrinos is that, okay, maybe we don't have to wait for one event, since we know that there's a lot of supernova exploding everywhere in the universe. So maybe if we collect all the neutrinos coming from all the supernovas, we can detect them, because they will make a diffuse supernova neutrino flux background. And so the idea is, instead of waiting for the next galactic supernova, try to detect this diffuse supernova flux. The problem is, of course, these diffuse supernova explosions didn't happen in our galaxy, so they happen anywhere in the universe, so the flux will be very low. Will be the geometric factor of 1 over r squared, but actually it will be worse than that, because the universe is expanding. When the universe expands, all the energy of the supernova neutrinos goes to lower values, and it makes life tougher to detect these low energy neutrinos. But anyway, if we integrate the idea, yes. I'll answer in the next slide, okay? But it's close by. We have to integrate all over, but it's I think it's between redshift 1 and 2, something like that. Right? Okay, so the idea is to integrate all the supernova neutrinos to compensate for the geometric factor. And before going further, we have to do the same thing that we did to solve the Ober paradox. And you know what are the Ober paradox? So what is it? Yeah. Yeah, excellent. So yes, that's the paradox, right? The 1 over r squared would be compensated by the volume integration. So we would have infinite luminosity anywhere on the sky that we look. So the sky should be, the night should be with a lot of light from the stars. We see the starting of this paradox when we look at the Milky Way, for instance. When we go to Atacama, where I've been last week, very nice, you see the Milky Way, and you see that, okay, you start to form this uniform background of light because of the many stars that contribute to the flux. But we know this is the solution to this paradox is we can start thinking about the retarded time, the same retarded time that we have in electromagnetism when we calculate those potentials and retarded time, because everything light takes time to propagate. So this time here is not the same as this time here. We have to take into account the time that the light exits the source and arrive at the Earth. This is one thing that we have to take into account. The next thing is that since the universe is not infinite in time, the integration should go only to causal universe. So it's not 0 to infinite, but 0 to causal connected regions. And finally, the universe is expanding, so photons redshift. So even if those two first things were not true, all the light from the very far stars will go into infrared, and we will not be able to detect it optically, and then we would have a dark sky at night. So the idea with supernova neutrinos is the same one. So the main ingredients are here also to calculate the flux of the neutrinos of supernova. And then we have the maximum Z, where this redshift, from where this information comes. We replaced the integral on the spatial dimension for the integral on the redshift, so we have to connect it with cosmological expansion. So the ingredients of these are supernova explosion rate. We have to know, when we can calculate this, and we are more or less confident how to do these calculations of the rate of which the supernova explodes in our universe. Then we have the neutrino energy redshift, which is here, the universe expansion, and what we get from this calculation, which is a kind of straightforward calculation, is some small window of on energy to try to detect the supernova. These are 3 different assumptions on the neutrino, supernova neutrino flux. But anyway, we have this window between solar neutrinos that would be a intrinsic background for energies lower than 20 mega electron volts, roughly. The atmospheric neutrinos, which dominate for energies higher than 35 mega electron volts. So this small window between 20 and 30, the main neutrino flux that's arriving at the Earth comes from these diffuse supernova neutrinos. So it's a small window, but okay, we have an opportunity to try to detect this supernova. The challenge, of course, is the event rate, which is very small. It's very hard. If you look at the solar neutrino flux, those high energy neutrinos are already very, very hard to detect, and they are much more numerous here than the diffuse supernova neutrino flux. So these neutrinos here are very hard to detect. They produce, I don't know, 2-3 events per day in Super Kamiokande. So we are talking about orders of magnitude below this. And we can find here different proposals to detect the number of events per 0.5 MeV per year. So we are talking about one event per year to have some spectrum information. Of course, if we integrate in the energy, we can have more events, but then we lose very important information, which is the spectral information of these neutrinos. But anyway, can be done, and we just have to, and now we have to wait, but since we have some experiments, we have to wait, but for different reasons. The neutrinos are already here, we just have to collect a lot of data with a lot of patience to try to overcome this slow flux that is arriving here. And this is a different kind of waiting than the supernova neutrino, right? This is there's nothing we can do here unless building larger detectors, neutrino detectors. Okay, my third topic that people maybe are waiting, it's being advertised sometimes that I will be talking about that. I hope I don't disappoint you, because I will not go into some of the details, but it's the high energy neutrinos. So we are going to the other part of the spectrum of these astrophysical neutrinos, which is the neutrinos with the highest possible energies that we can think about. And there are a number of different experiments collecting this data. I will focus on IceCube because IceCube, well, it's on headlines now. So, but to be fair, I should also talk about, for instance, Antares, which is also working, also collecting data, and it has a complementarity information with IceCube. But anyway, I will focus on IceCube and the latest data from them about this highest neutrino flux. Yes, Baxan also, yeah. Thank you. Anyway, maybe I'll repeat myself here. Probably you heard this in somewhere else, but I will say it anyway because some of you may not know the details of IceCube. IceCube is located on the South Pole. It uses, since we are talking about large, very, very, very large neutrino detectors, we must have we have to go beyond these constructions of Super Kamiokande and Dune, SNO, which is limited by the size of the detector. If you go to the ice of the South Pole, the size of the detector is limited only by the number of photomultipliers we have, because we have all the space there to bury photomultipliers, and this will determine the size of our detector. So what IceCube did was to place a lot of multipliers, photomultipliers strings inside this very clear ice, 2,000 meters below the surface level on IceCube, and then these photomultipliers will be able to detect any sharing of light that any charged particle will produce when it crosses this ice. There are a lot of some details of this experiment are the energy threshold will be determined by the separation of these photomultipliers. If we put a lot of photomultipliers really close by, we will lower the energy threshold. But if the idea is to build a lot, detect this very high energy, then we maybe it's not the best solution to crowd these photomultipliers. Maybe it's better to spread these multipliers in a larger volume. So IceCube actually do both. They keep a very what they call deep core with a lot of photomultipliers closer by to have a sensitivity to lower energy neutrinos, and a large volume with not photomultipliers more far apart from one another, that will be able to increase the number of events for the highest energy where the flux are lower. The usual way to put the size of things here are the Eiffel Tower, right? So this is the Eiffel Tower, this is the size of the detector. So it's a very large detector. And it detects neutrinos with two main channels, which is, for instance, if a muon crosses, an energetic muon crosses a detector, it will produce Cherenkov light, and the Cherenkov light will leave a trace which will very easily establish the direction from where the muon came. So if this muon were produced somewhere here, here, from an electron neutrino, then, a muon neutrino, then this will be a sign of detecting this muon neutrino. But the problem is to know now if this muon neutrino comes from some extragalactic source, or if it comes from the atmospheric neutrino flux, for instance. It's one important step in the analysis of the data analysis is to disentangle what is atmospheric neutrino flux, what is not atmospheric, and this comes from the spectrum shape of these events. But anyway, this is what we call the track event, a track produced by the Cherenkov light of the charged lepton, and a hadronic shower here where the charged lepton were produced by the neutrino. Okay, but if we are not talking about muon neutrinos, if we are talking about electron or tau neutrinos, the electron neutrinos, for instance, the electron produced by electron neutrinos will not propagate into the ice. It will be very fast, will be absorbed by the matter. So it will not produce the track. Tau neutrinos also will not produce the tracks for a different reason. It will decay much faster, then this track will be absent. So the topology of electron and tau neutrinos are very different from the muon neutrinos. It's more like a spherically symmetric shower of Cherenkov radiation. So one thing that we can conclude is that this kind of event loses directionality. We don't know where these events comes from, while the track events have a very good angular resolution for the incoming neutrinos. So the angular resolution is better than 1 degree, which we learned today, which it is a good number, right? So we can determine these high energy neutrinos with a very, very, very good precision on the direction. So we can point other telescopes to that direction to look for something else, for instance, right? There are some problems of this detection. One of them is that some of these events are not contained. We don't have a large enough detector volume to contain the muon, and sometimes then the muon goes out of the detector, and when it goes out, it carries energy, and it's harder to reconstruct the energy of the incoming neutrino. This is one of the problems. The other one is the huge atmospheric background, which I already mentioned. We have a lot of muonic neutrinos coming from these energies around some giga-electron volts that will make it harder to disentangle the muonic neutrinos from the astrophysical neutrinos. And also, at such high energy, the highest energy, the neutrino absorption on Earth starts to be relevant again. So it's not that all the neutrinos arrive at the ice cube, the ice cube detector. The most energetic neutrinos will only be detected if they come from above and not from below. Those very high energy neutrinos coming from below will be absorbed by the neutrino, will not arrive at the detector. So mainly we are looking the highest energy neutrinos, IceCube is looking at the south hemisphere. It's looking up from the south, right? Okay, the shower events can do a much better job in reconstructing neutrino energy, since everything is contained inside the detector, so it's just a matter of counting how many photomultipliers gave the signal and integrate it to the total energy. However, they have a very poor directionality, less than 30 degrees, which we also learned today, which is very bad. It's very hard to use these events to pinpoint anything in the sky. But they have a cleaner background, because at they are not present, electronic and tau neutrinos are not present in very large energies coming from atmospheric neutrino flux. So we don't have to worry that much about the atmospheric neutrino background for those shower events. The IceCube runs that we got are those here. The last one published is from 2017, October 2017, taking data since April 2008. So there's a lot of different configurations, different techniques, different software to clear the backgrounds. And this is the latest result presented at Neutrino 2018. The pink ones are the new events of the last 1.5 years, and the black ones are those from the 6-something years. And we have then, this very energy is going up to 10 to 3 tera-electron volts. Most of the neutrinos here are around 10 to 100 tera-electron volts, and this is the distribution of the events that we have today on IceCube. This is presented on Neutrino 2018, so it's still preliminary. The black events already have gone through all the analysis, but the red ones are just out of the oven, so they are still working on these numbers, on these events. But anyway, what is happening with the neutrino flux is, first let's talk about the arrival directions. All of them are, well, we have the background of atmospheric neutrinos, and all astrophysical neutrinos that IceCube are detecting are coming from where we expect, which is from above in the South Pole. So these high energy neutrino events were present also here, but they got absorbed in the Earth. And the excess of neutrino events, of course, it's on high energy to overcome the atmospheric neutrino background. So at this highest energy, the atmospheric neutrino background becomes lower than the signal of these very high energy neutrinos. So we can, with much confidence, say that these guys here come from some astrophysical source. Okay, so we have all these events, and let's see what, right, all these events, and let's see what we can do with this. So one of the main concerns about astrophysics, neutrino astrophysics, is what is the spectrum of the neutrino, because this will give us an idea what was the acceleration mechanism. We always like a Fermi acceleration mechanisms or something like that, some power spectrum. So one thing we can do with these events is try to find to fit some power law and see what is the index that we come from these fits. And with these events, we have something like 2.2, 2.4 on the power law of the spectrum. This is a lower number, so it's less steep than the atmospheric neutrino flux, which is 3 point something. So that's why we can detect these guys above. We can disentangle these guys from the neutrino, the atmospheric neutrinos above some energy. And with some observation here, up to the Neutrino 2018 conference, we have no directionality of those events. Of course, this I'll come back, obviously, on that, but they said on Neutrino 2018 conference not much ago that they couldn't find any preferred direction where these neutrinos were coming from. So this was the conclusion until very recently, but of course I will come back to that. And what about the flavor composition? The flavor composition also is something very important because, again, we know these neutrinos mixture and convert flavor into one into another. So if we have a clear picture of the flavor of those neutrinos, maybe we can access the production mechanism, because the production mechanism, different production mechanisms will give different flavor compositions. So, for instance, if the neutrinos are produced through pion decay, we already know that this is the base of atmospheric neutrino problem, that we have 2 more neutrino from the muon than for the electron, so we have this kind of sharing between the flavors, but this is the production. Then we have to put this into the oscillations. Then we have those oscillation probabilities, and who was doing the exercise yesterday about how much this number will change, I already know what we'll have here, right? Who got the number right? Who was there? Nobody? Okay. I know some people got the number right. So this number, the amount of electron neutrinos after oscillation of this composition will not change much. We will have the same number of electron neutrinos. I don't know how I see people. And some equipartition of the muonic neutrinos and tauonic neutrinos. So this will be the sign of some production mechanisms like the pion decay. But we can have other kind of things. For instance, let's say that this the muon after the pion, the muon produced by the pion is somehow the energy is dampened before decaying. Then it will decay eventually into electron and electron neutrino and another muon neutrino. But these energies could be lower, and then we would lose this information. So we, in principle, could have a pure muonic neutrino production. Or let's say have some decay, radioactive decay of electron neutrinos producing a pure electronic neutrino initial flavor. This guy, again, will evolve because of oscillation, and then we have something like that. This pure electron will be 1.6, 2.6, 2.8, pure muonic neutrinos, 0.6 to 1.3, 1.1. So they are, in principle, distinguishable, this reproduction mechanism. Of course, we don't expect anything that simple. We expect something much more complicated happening in those very high energy astrophysical environments. But it gives us a way to understand how the ice cube can try to differentiate between these neutrino production mechanisms. Okay, so it's reasonable to expect 1-to-1-to-1 on Earth, and this is the kind of analysis that ice cube are doing and presenting the results. We have here, it's a triangle that sums up to 1. The way to read this triangle is, let's see this point here. This point here produces between 0.33 and 0.50 of tau neutrinos. Little slight lower than 0.50 muonic neutrinos, and we get here 0.17 of electronic neutrinos. So we follow the slope of the numbers to see the amount of different neutrino flavors that are here inside this triangle. So these points here are the examples that I showed on the last slide. So, and this would be an initial muonic neutrino flux. This will be an initial electronic neutrino flux. This will be an initial pion decay. And the best fit point is here, pure muons, but with a large, for now, large allowed regions for anything other than these very extreme cases. But anyway, it's interesting that IceCube is already producing this kind of plots, but it's not a very robust analysis. For instance, this is the analysis done with all the data, the 7.5 years data. But if we take out the last 1.5 year, the best fit point comes to here. So this was the best fit point with 6 years. This is the best fit point for 7.5. So okay, it's not a very robust analysis because they are still collecting data. But the expectation is that in the future they will be able to distinguish between different production mechanisms based on the flavor of the neutrinos that come on Earth. This is also something that, for instance, non-standard neutrinos will mess with the interpretations. For instance, remember yesterday I talked about, for instance, decoherence and relaxation effects, non-quantum mechanics playing on neutrino evolution. And then, for instance, if we have a relaxation, we would have, for any initial flavor composition, we will have equipartition. So we will always go to the center of this triangle. So if, for instance, a little bit of speculation, if we go out of this, if the IceCube says that we should be around here, we could start to constrain things like decoherence relaxation effect. But anyway, this is just the first step. For instance, we are still on the starting to make this analysis. So, for instance, now it's just they are just proving that this will be a usable tool in the future. Okay, this was the scenario until some weeks ago, and very recently, then they published on Nature, and they announced it to everybody that they had a very energetic neutrino, muonic neutrino, in concordance, coincident with flaring blazar observed by other telescopes. So it's the multi-messenger events that's happening, and it was already mentioned by Marcelle. And then we have this 219 tera electron volts neutrino event coming from the same place where this blazar TXS 0506 etc. Were there, right? So we have this is a strong indication that those two events are related. Those neutrinos were probably those neutrino, it's one event, were produced on this blazar by some mechanism. And this is the event, is the real event that triggered this analysis. The neutrino comes from the blue. I forgot to mention, blue means early, yellow means late. So those events happen early, and then those photomultipliers triggered, and then those are triggered late, so we can construct the direction of the incoming neutrinos. And we have, so here, early, late, and the energy reconstruction leaving 200 to 219 TeV. And it came, they got lucky because remember that these very high energy neutrinos must come from above, not from below. It came from below, but very close to horizon. So it's escaped the absorption of the Earth, because it came very close to the horizon, only 6 degrees below horizon. So it arrived from below in the IceCube detector. Okay, and so this event triggered the let me go back to the paper. Triggered the other telescopes to look for some counterpart, optical counterpart. Actually, Fermi-LAT was already detecting this blazar for some months, since April. And so they already know that that object was there on the sky, so they have a good match. Okay, this neutrino comes from that event. And later, MAGIC, another telescope, detected a gamma ray burst from the same region. So we have a lot of different informations coming from the same with the same event. And after that, so what happened chronologically was we had one event. The IceCube said to people, okay, people, telescopes, what else we have there? Fermi-LAT said, okay, I'm watching, I'm detecting this blazar for some time. MAGIC says, okay, I will look for there. Oh, look, I'm seeing gamma ray bursts. And then the IceCube after that started to look again to the data recorded to see if they missed something when they claimed that there was no directionality. So they went back to all the data that they recorded on the 7 years, and they found an excess in some time window between September 2014 and March 2015. And you already had a spoiler of what I will show here, but anyway, I will show it anyway. So what they have was first phase, nothing special. Here we have the date and the probability of something some directional information that indicates a possible source. So no probability that we have a preferred direction on the first phase, nothing on the second phase, nothing on the third phase, nothing on the fourth phase, and finally on the fifth phase, here's the jump on the probability. So it is not a signal that is spread over time, equally over time. It's concentrated on this, and then it disappears again. 2016, 2017, nothing happened until the one event that triggered the analysis again. So here we have, I didn't mention the events. Here we have 13 events in excess, and here we have that one event that started the reanalysis. And if we take everything together, that's what we have. These events obey a power spectrum, are well fitted by a power spectrum, with a power index around again 2.2, close to, these are only the events that comes from this region, but then it's close to what we have with the full data sample of IceCube. So any acceleration mechanism is producing something with this power law around 2. And the announcement they made, it was a very nice announcement. If you didn't see this video, I strongly recommend, because it's the idea is to stress the multi-messenger characteristic of this kind of analysis. So they got on the to speak Francis Hausen, which is the IceCube principal investigator, Regina Caputo, Fermi-LAT analysis coordinator, Hazmik Mikzoyan, MAGIC spokesperson, and Olga Botnev, former IceCube spokesperson. And they talked on this particular order because they obeyed the chronological way that things happened. First, they saw one very energetic events. Then Francis Hausen told us about this event. Then Regina talked about the Fermi-LAT that they were seeing this blazar for some time. Then Magic said, "Oh, okay." Then after you told us to look on that direction, we found some gamma ray bursts, and finally, IceCube came back to the old data and found those 13 events. This is the chronology that things happen. It's not the real chronology that will go into the textbooks, right? Into the textbooks, we first will have the 2015 events, then we'll have Fermi-LAT, then we'll have IceCube highest event, highest energy event, then we'll have Magic confirming with gamma ray bursts. But it's a nice way to present the results, and everybody together here, stressing that the word of the moment, okay, 2 words of the moment, is multi-messenger. So we have this happening with neutrinos, high energy neutrinos. We have this happening with the oscillation, with Marcel talk about the gravitational waves and other multi-messengers companions. So this is the most important lesson that we take from here. And I'm not sure if it was André which says that. This is a suggestion to everybody that is starting to study things now. Things are multi-messengers, so you have to be multifocal, right? You have to don't specialize too much on a neutrino or dark matter or cosmology or astrophysics. The best way, since all the information are coming from very different sources, you have to know everything. So, yeah, for sure. Yeah, okay, specialize in everything. Yeah. So that's it. The conclusion I have is that work in progress, and we are having progress. We are making progress. So thank you.
Thank you, and we'll go to the questions. But before I will announce a small change in program, as you know, there is a total eclipse today. We were not very hopeful of seeing it, but a group will be in the parking lot of IFT, which is behind this other building. We can go all together there. That's the plan. But the totality ends at 6:13, and that nice part is the total. So the idea is to have 10 minutes to see the totality. So we will end half an hour earlier. And thanks to Pedro that he left a bit of time for us. And so we will end the question sessions 15 minutes earlier. We'll have a coffee break 15 minutes shorter. And then we'll be just in time to leave and rush from here at 6 to see the end of the totality. We are not sure that the wound will be the right height. So don't be too enthusiastic, but let's be hopeful that we'll see it. Okay, so now we go to the questions, first to Pedro, and then we go to the questions for all the speakers that are here, okay?
I don't know if Pedro knows, but it seems that Supernovae is putting ahead the gadolinium now, and because why they put gadolinium to be more efficient to detect neutrons, and then they will be more efficient than neutrino detector for the diffuse neutrino supernova. And then they already put it, and they are beginning to operate in this way for 1 or 2 years to get the sensitivity to see for the first time diffuse FUTs.
Okay, excellent.
Actually, there are 2 questions. The first one, in the first slides, you were talking about the supernova neutrinos, and you showed 3 graphics about some stages of the supernova. And in the accretion part, at the very beginning of the graph, there was some difference between the flux of electron antineutrinos and electron neutrinos. Why that happened? And the second question is, how do they made the calibration of IceCube? Is there any source of neutrinos nearby that they used to make that, or we use data from other experiments?
very well this. Sorry. You know very well the microspectrum of the muon decay. You see this events, then you calibrate the detector. But also the superconductor before they begins, he calibrated to see electrons because they use a LINAC from an old hospital. This was the job of Kajita. He went there to calibrate the superconductor for electrons, using a LINAC. And they know very well for these very low energy events.
And yes, that's it. And about the first question, well, they are electron neutrinos and electron antineutrinos doesn't have the exactly the same interactions. So, for instance, if we do if we write the diagrams of electron neutrinos or antineutrinos interacting with protons and neutrons, they have some differences. So these differences reflect on the production of electron neutrinos and antineutrinos. Also, it doesn't have positrons inside the supernova. So, yeah, there are some different aspects of the interactions that leads to this difference on energies and total flux.
Does stellar formation history alters the expected diffuse neutrino background?
The spectrum, well, the total flux for sure. We have one of those ingredients which we are just confident about the theoretical predictions, but we are still some uncertainties, is the rate which the supernovas explode. And not today, but during the whole history of the universe. Well, not the whole universe, but because the main contribution comes from Z up to 2 or 4, something like that. The spectrum, yes, again, we still we have confidence about the main features of the spectrum, but then we have all these things happening inside the supernova that, okay, it should be at least the sum of all neutrino flavors should be close to thermal in some way. So since we are only looking for one part of the spectrum, it doesn't differ much from what we had on that graph.
So maybe I can comment on that. It would change the spectrum if you had a completely different shape of the star the star formation rate is basically the supernova rate, right? You have convolved with initial mass function. And then if you were completely wrong on where it peaks, it would change the energy because it would peak, say, at redshift 2 instead of 1, and then you change the redshift of the neutrinos. But the uncertainties that Pedro are mentioning are not like you have a bump at 2 or you have a bump at 1. You are confident more or less on the shape. So eventually it does affect, but it doesn't change dramatically the shape of the spectrum.
Can shock wave change the neutrino transition?
The shock wave inside the supernova?
Yes.
Yeah. Well, they must be there to. Well, the shock wave is a fundamental ingredient of the supernova explosion. So, but it will not affect the neutrino flavor because all the neutrino, the flux of the neutrino are the thermal characteristic of the flux of neutrino. It's inside the neutrino sphere, right? So I don't believe the shock wave will change any of the main characteristics of the neutrino flux. Maybe some very non-adiabatic transition, but I don't think that will be the case.
And they also interact. I mean, you can't create the explosion of the supernova if you don't put in the neutrinos. So the shock wave is created
the shock
by
wave
the neutrinos.
is the neutrinos.
It's created by the neutrinos to a certain extent. So the details depend from what Pedro was saying.
We saw in the morning class that the density of the dark matter, the uncertainties in the density of the dark matter. Can I ask him a question, or?
Yes, we can open now to all the speakers.
Sorry.
Yes.
I thought we already opened up. Sorry.
I was planning to do this after your question, so.
Okay, maybe I can ask later.
No.
And there are many density profiles that you can see in the literature, and they are slightly different. How to choose which one is the appropriate one?
Maybe this is what I wanted to talk about in an additional class next week, if you want. But there is 2 points. So you have performed the exercise that I gave you, no? The one where I was asking you, what is the density profile that you need to make a velocity curve become flat in this region, okay? So I stressed at the end of the other class that you need, well, at the beginning, that you need a density profile like r to the minus 2. I actually was watching myself on YouTube and I said it's exactly what found from simulations. Not exactly what found from simulation, but to a very good extent. And I also said that in the center is much more complicated. So this is true here, that this is what the dark matter profile is, but in this region where the baryons, where the stars dominate the profile, is not really clear. So first of all, you don't choose a profile just because simulations tell you what it is. Dark matter collapses in the center in a complicated fashion. Stars are forming, and you know that the density profile must be something of the kind. So say that you believe the simulations and you know that the physics is implemented correctly, then you don't know to which extent. So here, say that the disk is over here, 10 kiloparsec, so somewhere around here, but then it is not clear whether it's flat, whether it goes up, whether it bends flat but not quite, okay? So which one to choose? That's your question. You don't choose any. You have to look at you have to go and find if there are data. It depends on what you're doing, okay? If you are doing an analysis of if you want to know the real cross-section, say for direct detection, and we are sitting somewhere around here at 8 kiloparsec from the galactic center, you want to use the data. So you take the real rotation curve of the Milky Way, then you take the real distribution of stars of the Milky Way, and then on the top of it, you fit a profile, and you will get something with error bars, and you use something with error bars. Of course, you can use the central value. Someone suggested the galactic center for indirect searches. Then you have to use rho square at r, where r is close to 0, right? So somewhere around here. The uncertainty from the data on that is basically everything. You can extrapolate down, but that extrapolation doesn't really mean anything. Okay? I can go to a seminar on this if you want, if you are interested on the subject. And the point that we are trying to make now, people know that you have to bracket. So what people do in the literature say, okay, I take a pure NFW, which name could say something to some of you and not to others. And then I see what happens if I take something with a flat profile. And then I see what is the signal that I expect in the 3 cases. But then if I am seeing no signal and I want to interpret it, the interpretation depends on what you're using. And that thing you're not allowed to choose if you have to take the real data. The real data have error bars around here are like this. And that's very depressing.
Okay, so it is with respect to the dark matter annihilation inside the sun. And in this case, and looking through the neutrino branch, what would be the flavor that would be produced by this process?
It depends on how your dark matter is attached, is connected to the standard model. There's many candidates. It depends how they're coupled to the standard model. They will annihilate. Will be a branching ratio and certain flavors of neutrinos. The interesting thing is that, as I might have mentioned, but I want to make clear, I am looking at a high energy signal, okay? So I am looking at something if I am looking at a WIM scenario and I expect this thing to happen in a WIM scenario and then it happens, I'm looking at a scale of approximately 100 GeV, okay? 10 GeV, 1 TeV, but this. it really doesn't matter what the flavor is, because I don't expect anything like this to be produced in the sun. So if I find something like that coming from the direction of the sun, Pedro, you correct me if I'm wrong, but that's already great. I don't have to really distinguish between anything, because there I really don't expect anything. The nuclear neutrinos are at 10 MeV or something like that. So that's really the amazing part. And what flavor would you expect? It really depends on the model. But first look and see if you find it, and then, and then you.
And also, independent of the flavor you produce, you have those contaminations to the other flavors because of oscillation. So probably, for these values of energy, you will have equipartition, close to equipartition of flavors.
You have neutrinos from this because when you have the atmospheric cosmic rays hitting the sun, when the cosmic rays hit the sun, they produce neutrinos of this very high energy.
The corona.
Huh?
The corona. You're talking about the Mirizzi paper about the coronas, that there are cosmic rays that upscatter on the corona of the sun.
Yeah, they scatter. Yeah, in the upper,
Yeah, but these neutrinos are produced in the very center of the sun. So we're talking about science fiction, but if the process for which dark matter gets accumulated in the sun and then annihilates into neutrinos, this size where the annihilation happens effectively is 1/10 of the core of the sun in terms of radius. The core of the sun is 1/10 of the radius of the sun. So the annihilation and the production of these neutrinos will be concentrated in 1/100th of the sun, of the size of the sun. I assume you don't have such a good directionality, so you might get mistaken with what is produced in the corona, but I thought it's not overleading. So what you expect from this process is bigger than what you expect from the corona, so if it happens at all. The cosmic ray is hitting on the solar corona, right? The cosmic rays cannot enter the sun. The cosmic rays will stop somewhere around here, right? Because the sun is the sun. There's a lot of stuff. Yeah, but they enter up to here. They decay. The sun is very big. So all of this happens around the surface of the sun. This stuff is 100 concentrated inside.
Fabio, can you comment on Dama results and nano modulation?
Okay, so that's stage. So he asked me this morning. I said, "Oh, why don't you ask in front of everybody so I can do it only once?"
We will let Fabio answer, but just recall that this will definitely will mention during next week, because they will show all these plots.
But before getting to the Dama results, that gives me the chance to mention one thing that I did not mention into the class. So I said that the rate, it's written here, right? The rate is proportional to whatever is that I want to observe. Okay, and it's given by nature. Then there is the experiment, and then it depends on the density of dark matter around myself and the velocity. It's a flux. Okay, actually, the dependence of the velocity is complicated because you have to integrate out the distribution velocity, and you will have a lower threshold and an upper threshold because it's the threshold for depositing energy into the detector, etc., etc. But there is one interesting feature. Say that we are sitting on the sun, which already is not true, but the sun, we're sitting on the Earth, but the sun is moving in the halo, so there is a relative motion between the velocity distribution of the halo and the sun that is moving into it. But that's a fixed thing. The halo is a virialized thing, and the sun is moving into it. But whatever is the velocity of the sun toward the halo, this is what I will put in here, okay? But there is one detail. We are not sitting in the sun. We are sitting on the Earth, which is going in a almost perfectly spherical orbit because the ellipticity of the planets is very small around the sun. Okay? So that means that, say that I'm on the 21st of March, I'm heading toward the halo of dark matter particles, and on the 21st of September, heading back. So the actual velocity perceived by my detector will be the central velocity of the sun plus or minus this delta V, which is the motion of the Earth around the sun. Okay? So if I am to expect any signal from dark matter, and I am good enough to observe it, if I have my detector is a God detector, I should see not only a signal, but a modulation in the signal that goes with the season. The DAMA experiment claims not only to have seen the signal, but to have seen a modulation of the signal. So first of all, I think this velocity is at the order of 10%. 10% more or less? Well, you can do the calculation because you can take the orbit of the Earth, compute it, and the typical velocity is 100 kilometers per second, so you compute what's the velocity of the Earth around the sun. That's 10% of the signal. So first of all, that means that they've seen the signal and they have control over the first or the second digit, because if they're able to see modulation, that means the modulation is at the level. Second, they claim that this modulation is above 7 sigma now, right? Or 10, or maybe, yeah. So, and it's in phase with September, March, which is the equinoxes, so when our velocity is maximum. The thing is that the data seem to be there, and they claim to have performed extensive checks. But, so they haven't released the data. But it's clear to everybody that they've seen something. Nobody is claiming that they haven't seen something, they're just faking the data. That would be completely crazy. The point is that they're not releasing the data. And let us say that they are right and this is dark matter. Everybody thinks it's another sort of system. They've seen something, there must be something. Of course, if DAMA is seeing it, everybody else should be seeing it. Okay? Including an experiment which is sitting literally no more than 5 meters away from DAMA, which is xenon, and they have not seen it. Okay? So either is some such bizarre candidate that you're seeing it with the material which DAMA has done, which is argon, right? I saw you ion, yeah, in the crystals, the famous crystals. And it's not seen in xenon, neither in all the other experiments on the Earth, or there is some bizarre effect in these crystals, which was the tunneling effect that was studied, but really nothing seems to be able to mimic this. So I myself believe that DAMA has seen something. It's probably a bizarre isotope which is activated from the modulation of cosmic rays, which is known to happen because the size of the atmosphere changes with season because of the variation in temperature. And it's a bizarre isotope that is sitting in the Gran Sasso, something. But in my opinion, it would be, so that would explain the modulation, right? But in my opinion, it would be extremely bizarre if they had seen dark matter and nobody else hadn't. And at that point, the collaboration should release the data. I don't know what your opinion is.
No, I agree with Fabio. So there is just one thing I want to add is that so people have exhausted the nuclear physics, cosmic rays, anomalies, and so on, possibilities. And none of them also, so far, are capable of fully explaining DAMA signal. So even these temperature modulations in the season is not enough, is enough to explain the modulation, but not the amplitude of the modulation. So always, all the assumptions you've tried so far, they fail at some point. So it's really bizarre. I mean, I have no idea what it is. So, and I agree with Fabio. I think just not Fabio and I, 99.9% of the community, we agree on that. But I don't know. I mean, we don't know what we can get from this. I mean, what's
thing is that obviously what you should do to see if it's an environmental effect, we don't know what it is. Everything we know in terms of nuclear physics, non-cosmic rays. So first of all, they might have seen new physics. And this might give them a Nobel Prize even if it's not dark matter, right? If you've seen new physics, you've seen new physics, fantastic. The thing is that to disentangle this from the environmental effect, you should build the same experiment or bring the same experiment in a different environment, period. There's no other way around. The thing is that they don't want to do it. And they, for a long time they said nobody can grow the crystals because growing crystals is apparently an art, it's not even science, because the copyright for making them was sold, the enterprise. Now again, apparently it's possible. So what many people have been advocating, well, and there is another thing. If they've seen new physics and you experimentalists build the new experiments just to confirm that, very likely you are not going to get the Nobel Prize. So why to build an experiment to so either you confirm the other experiment and they get the Nobel Prize and you don't, or you disconfirm the experiment and then you don't get anything because you're just... So people tendentially don't want to build another experiment, don't want to build DAMA 2 unless it's the same collaboration. I think that there was a problem with the credibility of the principal investigator of DAMA at the time the data were released. That was not the most the rightmost person to present the results. It was a person that could start crying during a conference, so that there were sociological issues related to the presentation and the credibility of the results. And the fact that they don't release the data, it's also something that doesn't add to the credibility of the experiment. But since another, there are underground laboratories being built in other parts of the world, and that would be a nice suggestion for one of the experiments that could go in these new underground laboratories in different continents and in different hemispheres.
Sure, that's already a publicity for the workshop right after the school, which we will repeat again next week. Just also another publicity is that we have, one of the experiments does have a sodium iodine detector. It's not a DAMA detector because they don't let people reproduce this. There are groups interested in doing that, but that's a sodium iodine detector. So if you want to have an idea of how this kind of detector works, that is claiming this dark matter detection, it's the experiment number 1. That detector is very commercial, of course. It's not these huge crystals, but it's the same medium. So it's experiment 1, just out of curiosity.
So let me just add one thing before she starts. On the theoretical side, so this then is not just 99% of the community, 100% of the community would agree on, is that today we don't know, there is no dark matter model whatsoever capable of explaining DAMA signal and be consistent with the existing data. So even the people from collaboration, even the spokesperson from DAMA would agree on that. Okay, so today, so might be something very bizarre, I don't know.
Do we have an idea why there is such a difference between the observers, between the Hubble constant, between the type 1A supernova and the Planck observables?
Now you're asking about the discrepancy between the determination of the H0 that Marcelo showed, the one determined by